Good evening. If you have a mobile, if you'd like to put it on silent, please. Thank you. Very warm welcome back to Dr. Peter Kay. He came here probably about 4 or 5 years ago. This time his talk is an introduction to the body's defence and repair systems and how they affect development and treatment of cancer. Highly qualified Peter has worked in Oz for many years in immunogenetics, publishing many papers relating to genetics and cancer. He currently runs a clinic as a support for cancer sufferers. He's also acutely interested in providing health education based on science-backed research. Please welcome Dr. Peter Kay.
Thank you very much indeed for that good introduction, Rob. Today I'd like to talk to you about all sorts of different factors, biological factors, that influence whether you get cancer and whether a treatment you're given is going to work. And I'll introduce you to quite a number of very exciting ways in which the body's consistently repairing itself and defending itself. What I would like you to do is, please interrupt me at any time and ask any questions you wish, because I really appreciate responding to you. So that's the topic I'm going to talk to you about today. This really is just a summary of the kind things that Rob said, and I want to make the point that I do have an educational program which I'll tell you a bit about more at the end. First of all, to give you an idea of what cancer is all about. Many tissues in our body are continually being repaired and replaced. So cells have to actually divide and then form different new cells, and they only last for a certain time and then they die. Now, there are systems that tell a cell when it has to divide, and a system that tells a cell when to stop dividing. Usually there are many different kinds of genes that make proteins that turn on the cell cycle. It makes a cell divide, and these are called proto-oncogenes. They control cellular proliferation or cellular growth. There is as you can imagine, when a cell has divided, there must be a limit to the number of times that it can divide, or else you'd form a tumour. So there is another set of genes that actually make products that control the cell cycle, and these are called tumour suppressor genes. And in fact, in many ways, it's mutations, different kinds of mutations in both the proto-oncogenes and the tumour suppressor genes that play a very significant role in the development of cancer. For example, if something happens, a mutation or something like that, that turns on in the wrong way, if it turns on the expression of proto-oncogenes, they're then called an oncogene, and that causes the cell to keep dividing. There are also mutations happening all the time with genes that make proteins that slow the cell cycle down. So these are mutations in the tumour suppressor genes. So these are the main ways in which cancer is caused. Now, this diagram here, I know it looks complex, but what I want to make the point that in this section here, in your stomach, in your intestines, for example, continuously there are new cells being made. And each cell in the stomach lasts for about 3 days. So every second there are billions of new cells being replaced in your intestines, for example, and also in other tissues in which tissue regenerates. There's continually new cells being produced. And I want to get across here the idea of stem cells. For example, this depicts the lining of the intestines, and every single second of the day there are stem cells in the bottom here, and when their turn comes to divide, they do so and make what's called a precursor cell, and this cell then further divides to form the final functional cells that line the intestines. Now, it's these stem cells that I'll tell you much more about, because if these stem cells actually, if mutations occur in any of those tumour suppressor genes or oncogenes, then when they come to actually divide along this pathway, they don't stop, and you get a tumour. This next slide, this next slide summarises very briefly exactly what happens with respect to cancer. In this part here, these are stem cells, which often many stem cells are lying dormant in the tissue that's going to be regenerated for years. And when it comes their turn to actually multiply and divide and form new tissues, they go into this phase. They make progenitor cells, and then they multiply to the right extent to form the fully functional cells, say for example in the skin, liver, or regenerating tissues. Now, as I'll point out a little later on, there's massive amounts of DNA mutations occurring continuously, and sometimes they occur in a stem cell. But if that stem cell is laying dormant, it's not a problem because it's not dividing. But if, for example, a stem cell gets mutations like here, that will, when the turn comes for that mutated stem cell to divide, it goes into a situation like this, and it produces more of the stem cells that have got the mutation, as well as these abnormal cells that in fact continue to multiply, and that's how a tumour is formed. But you see, because, and this will become apparent a little later, because these stem cells they divide very rarely. When they have formed a tumour, because they're not dividing so extensively, chemotherapeutic drugs and the like don't have any effect. And it's these stem cells that cause the real damage by spreading elsewhere and causing secondaries. And so even if you're given chemotherapy in these stages, there's still stem cells released which can form a new tumour. And stem cells are really what needs to be got rid of. Right, I want to tell you a little bit about DNA, because that's the building block of all genes. Now, surprisingly, DNA is a remarkably unstable chemical, and its mutations can occur in DNA, or changes in the sequence of DNA can occur by a number of different ways, by cosmic radiation, which we're all exposed to right now, continuously. Things like toxins, we're always taking in toxins, and they can damage DNA. other radiation. Viruses play an important role in damaging DNA, and there is a chemical alteration in one of the particular building blocks of DNA that's required for lots of biological functions of DNA, called DNA methylation. When certain building blocks of DNA are methylated, they become unstable and they can spontaneously mutate all the time. So the point I want to make here is that continuously in all of us, we're getting massive amounts of DNA damage continuously. And I will tell you about systems that we have to repair that, and what should really happen if the repair systems don't work too well, because that's all relevant to cancer. As you can imagine, there's massive amounts of damage occurring spontaneously in all of us, in every single cell in our body. So it's not surprising that the body has developed well over 100 different genes that are involved in DNA repair. A little bit about DNA and mutations. As you probably are aware, there's 4 basic building blocks, A, G, C and T they're known as. Now, since the human genome, or all of the human's DNA, was sequenced finished being sequenced at the turn of the century, it was found that in every single cell, we inherit about 3 billion of these building blocks of DNA, a long sequence of 3 billion from your mother and 3 billion from your father. So in other words, there's roughly 6 billion nucleotides in a precise sequence in every single cell in all of our bodies. And these cells, the sequence of these nucleotides, have to be absolutely precise to keep everything in order. So, going back to the DNA repair systems that we have, when I pointed out that there's about at least 100 of them, they're all needed for many aspects of repairing these constant DNA mutations. And as it turns out, there's something about every single second in every single cell in our body. There's about 10,000 nucleotides being replicated. So in other words, in each cell, there's 10,000 in a linear sequence of DNA being newly synthesized every single second. And these DNA repair genes have to edit all of those sequences very, very quickly to make sure that the cell the new cell that's formed is it works properly. So you can imagine there's so many opportunities for DNA mutations to not be repaired, and you can imagine how common it is for cells to get mutations and form cancer cells. So it's a remarkable system. So DNA repair is an incredible system. Now, if the DNA repair systems go wrong, then you can have, and if those mutations do affect genes like the tumor suppressor genes or the proto-oncogenes, then cell cycle control is lost and you go on and get a tumor. And I'll just give you an example here of one of the particular DNA repair genes. It's called BRCA, it's breast cancer related gene. And BRCA1 is one of the causes of one type of breast cancer.